All right, there isn't too much new in lesson 4.2. It is mostly just finding particular solutions, but from word problems using acceleration, velocity, and position. And so that's a whole lot of stuff on its own, so I'm going to walk you through a bunch of the really weird ones we saw in our last worksheet. But before we get into that, there is a tiny bit of new stuff. So the first thing is we know that if we remember our position function, they typically write it as s of t. And if we take the derivative position function, we will get our velocity function. And derive our velocity function, we get our acceleration function. And so using this for integrals, if we integrate acceleration, we will get velocity. If we integrate velocity, we will get position. So that's the first thing that we have to know about. Now the second thing is that for acceleration, they don't always give us a function for acceleration. However, a lot of times they will say that it falls due to gravity, or just it's falling. And if it references gravity, it will depend on if you're using feet or if you're using meters for your units. If you are using feet, we are going to say that acceleration is equal to negative 32. And if we are using meters, we are going to say acceleration is negative 9.8. The negative sign is because it's falling, so it's going closer to the ground, so decreasing, whatever. And these numbers, that's just the acceleration due to gravity it's physics stuff. That when we're in calc, so I don't really know where it comes from, but these are just the numbers we use. And with that, we're going to get into the problems. Now, I've learned my handwriting, again, is really bad, so I'm going to put the word problems on the screen through editing. But we're going to start with something simple. So the first one is a baseball is thrown upward from a height of 2 meters with a velocity of 25 feet per second. Determine the ball's maximum height. So the first thing that we do in all our word problems, what we're going to have to do is we're going to have to find our acceleration. And we can see here that it is we're talking about meters, so our acceleration is going to be negative 9.8. Now we're also going to want to find a point for velocity and a point for position. So we can use those as our points we plug in when, just like when finding a particular solution. So they say that it's thrown upward from a height of 2 meters. So if it's at a height of 2 meters, that's position. The height is position. So that means its position is at 2 meters. And because it's a height of 2 meters, and this is the starting time, it's thrown upward from a height of 2 meters, that means our starting time is going to be 0. And at 0, it will be at 2. At 0, it's thrown upward from a height of 2 meters. So s of 0 is 2. In terms of our velocity, it says our velocity is 25 meters per second when it's thrown. So that means that v of 0 will equal 25. Because when we start to throw, our throw is at 25 meters per second. So both of these are right at the initial throw, and these are our values. And so with this information, we could just proceed like normal. So, setting on the paper, we're just going to continue. So we're going to integrate a of t dt and integrate negative 9.8. Just like we did last lesson, just this time we're actually using different values for acceleration and stuff. So if we integrate a of t, remember I said it's going to equal v of t. And on the right side, integrating negative 9.8 will give us negative 9.8t plus c. Now we can plug in our velocity value, and that will give us 25 equals negative 9.8 times 0 plus c. Negative 9.8 times 0 is just 0, so that means that 25 is equal to c. And from that, our velocity function is going to equal negative 9.8t and plus 25. And now we can just continue again. We're going to integrate velocity, and that is going to equal the integral of negative 9.8t plus 25 dt. Now, integrating velocity, remember, that's going to give us position. That's going to be equal to integrating this. So if we integrate negative 9.8t, that will give us negative 9.8 times t squared over 2. But negative 9.8 divided by 2 is going to be negative 4.9. Now, integrating 25, that will just be plus 25t. And then we have to have a plus c1. But we could find our c1 using this point right here. So if we plug in s of 0 equals 2, we will get 2 equals negative 4.9 times 0 squared plus 25 times 0 plus c1. All of these terms with a 0 cancel in this case, so 2 equals c1. our position function is s of t equals negative 4.9 t squared plus 25t plus 2. Now, the problem did not ask us to find a position and velocity function. The problem asked us to determine the ball's maximum height. And so we have to actually, now that we have our functions, we have to think, what does maximum height mean? So maximum height means it goes all the way up, it hits there, and then it's going to go back down. What happens when it hits its maximum height? And the answer is that velocity is 0. For that 1 second, that is, or that split time, that's at the max height, velocity is 0, then it's going to go back down, velocity is going to be negative. So if we can find a time when velocity is 0, then we could take that time and plug it in to our position function to find the ball's maximum height. So what we're going to do is, I don't exactly have a lot of room left here, but what we would do is we set v of t equal to 0. And that will give us a value, which our value in this case, when v of t equals 0, t is going to equal 25 divided by 9.8. And we don't want to simplify this value. I know typically in calc class what we're going to do is we're going to simplify, or we're going to round or truncate to 3 decimal places, but we don't want to do that right here because we want it to be accurate to 3 decimal places in the final answer. If we round or truncate right here, it might not be accurate in the final answer. So we're just going to leave it as 25 divided by 9.8 for now. And then so we know this is the time that it's going to hit the maximum height. So if we plug this time into our position function, then that means that will actually give us the maximum height. And thankfully, this is calculator active, so we don't have to do all this gross stuff by hand. And this is going to be about 33.887. And we have to include units. This was all in meters, so it's going to be 33.887 meters. And that is our answer for this question. Okay, we got our next one here. This one says that a canyon is 1,600 feet deep at its deepest point. A silver dollar is dropped from the canyon's rim directly above this point. What is the velocity of the silver dollar as it impacts the bottom of the canyon? Now this one, you're basically going to have to create your own coordinate system for this. And so it could be helpful to draw a picture. So we have our canyon, we have our the bottom of the canyon, and this is where it's going to fall. You're going to drop your silver dollar from right here. And so basically what you could do is you could call all the way down here as this is x equals 0, or you could call all the way up here as x equals 0. That is up to you. The way I do it, I call all the way at the bottom as x equals 0. And so because of that, if we continue reading with all our information, it says that the canyon is 1,600 feet deep at its deepest point. So that means this whole height is 1,600. And because this is where the silver dollar is dropped, this is where it starts, that means we can get from this, we can get that s of 0 is equal to 1,600. So that's the first of the points we need. And it says that it's 1,600 feet deep. Because it's feet, we can also get our acceleration. A of t will equal negative 32. And now all we need now is going to be v of something. If we continue reading, it says that a silver dollar is dropped from a canyon's rim. Now, I got a Rubik's Cube here. Its velocity is 0 right now because I'm just holding it. If I drop it, that 1 second, like that split second where it's just there where I let go, its velocity is 0 because I'm not throwing it down. I'm just letting go. So right as I drop it, right as it stops, velocity is 0. And then so we can apply the same thing here. If you're dropping a silver dollar, it's the same thing. So v of 0 will equal 0. And with this information, we can actually go through all our process again. So the thing we do in these problems, as we saw in the last one, you don't actually care what it's asking you at first. You just find your acceleration in your 2 points, you solve for your position and velocity functions, and then you use those to find what it asks you. So let's do that here. We have a of t equals negative 32. We're going to do, as we always do, we integrate both sides. So integral of a of t dt will equal integral of negative 32 dt. This will give us v of t equals negative 32t plus c. We can plug in our velocity into here. This will give us that 0 equals negative 32 times 0 plus c. or c equals 0. And that means that our particular solution for velocity is v of t equals negative 32t. We can now continue. So integral of v of t dt will equal integral of negative 32t dt. If we actually integrate each of these, we'll get s of t equals negative 32t squared over 2, but we can simplify that 32 over 2 into just a 16. So negative 16t squared plus c1. We can now take our position point right there, plug it in for to solve for c1. So we will get 1600 equals negative 16 times 0 squared plus c1. This thing with a 0 cancels, so we get 1600 equals c1, or our position function will equal negative 16t squared plus 1600. And now with that, now that we have both of our functions for velocity and position, we can actually continue reading and find what it's actually asking us. So it's asking us the velocity of the silver dollar as it impacts the bottom of the canyon. So remember our picture right here. We want to know the velocity when it hits the bottom. So we know when it hits the bottom that s of t will equal 0. So first we want to find the time that it equals 0. So what we're going to do is set s of t equal to 0. And doing that, we would just basically plug that into our calculator or whatever. I guess this time we don't really need to because it's a simple equation, but that would give us that t is equal to 10. So now that we know the time that it hits the bottom, what we could do is plug that time into the velocity equation, and then we could find the velocity when it hits the bottom. So what we do is we just do v of 10, and v of 10, if you plug that in, you will get to negative 320. And now for our units, this was all in feet, so it is negative 320 feet per second. And that is how you solve this one. Alright, this next one introduces a new kind of concept, but we're going to proceed as normal, and then I'll show you the detour midway through of how it's weird. So, it says, with what initial velocity must an object be launched upward from ground level to reach a max height of 600 feet? Now, the first thing I notice is that it says it's in feet. So that means a of t will equal negative 32. Now, we do need our v of something equals something and s of something equals something. Now, they tell us that it's launched upward from ground level. Ground level is typically set as 0 because it's like the bottom of the world or whatever. So s of 0 is 0 because it's at ground level. And now it asks, with what initial velocity does it need to go from ground level to reach a height of 600 feet? Now, initial velocity, that means velocity at time equals 0. So we know that much, but we're solving for the initial velocity. So we don't have a value for it. So in this case, what we're going to do is we're just going to call the initial velocity v of 0 will equal v. V is going to be a constant. We just don't know what it is yet. But with this, we're going to proceed as normal here. And we're going to hit like a point where we're stuck. But there is more information. So I'll get to that then. So first we just proceed as normal. So a of t equals negative 32. Integrate a of t dt equals integral of negative 32 dt. Just like normal, we'll get v of t equals negative 32t plus c. And here, we can plug in v of 0 equals v. And from that, we will get v equals negative 32 times 0 plus c. This negative 32 times 0 cancels, so we get v equals c. It's not normal because we still have this this v, but we treat it like a constant, as I said before, because it's just what we're solving for. And we're just going to plug that back in as v instead of a number. So that will give us that v of t equals negative 32t plus v. Now we can integrate both sides. V of t dt equals negative 32t plus v, or we're integrating that. I forgot to write that, but yes. And now we get that integrate v of t, we get s of t equals integrating negative 32t, we will get negative 16t squared. And if we integrate v, because with respect to t, we will just get plus vt, and then plus c1. Now we can plug in our s of 0 equals 0, and that will give us 0 equals negative 16 times 0 squared plus v times 0 plus c1. And that will give us that 0 equals c1, otherwise known as s of t, is equal to negative 16t squared plus vt. And now, once we're here, it kind of looks like we just hit a dead point, whatever, and we're stuck here. We have a vt here, there's a v. The t is fine, but the v we don't know what to do with. This is the point that we realize we're actually given more information in the problem. Now, the problem tells us that what initial velocity does it need to be launched upward from ground level to reach a max height of 600 feet. So we know that at some point, position will equal 600. And at the same point, it said a max height of 600 feet. And as we talked about in the last problem, when it hit a max height, the velocity, it's increasing, it hits it, and it hits 0 for a second, and then it falls back down, and it's a negative velocity. So at the max height, velocity will be 0. So at some point, v of something is equal to 0. And so, we don't know what these values are, so we're just going to call it s of something and v of something. I'm just going to call it k. So s of k equals 600, and v of k equals 0. K is just some point, we don't know what it is yet. But what we could do now is we can use these. We could plug s of k into our position function, and v of k into our velocity function. And now this doesn't look like it's doing anything, but it actually is, and it's important. So if we look at this equation right now, like our position function, we get s of t equals negative 16t squared plus vt. We have three unknowns here. We don't know what s of t is, we don't know what t is, and we don't know what v is. But if we plug in s of k is 600 into our position function, we will get 600 equals negative 16k squared plus vk. And this actually leaves us with only two unknowns. And if we plug it into our velocity function's up here, I'm just going to plug it in down here, that will leave us with 0 equals negative 32k plus v. And so now we have two different equations and two unknowns, so we can actually solve for both unknowns. So I'm going to clean up the board a little bit, and then we'll get back to it. All right, now I simplified it a bit. We have all our points up here. We have our velocity and position functions, and we have these two equations we made before I cleaned up the board. So on this equation over here, which we got from plugging in v of k equals 0 to our velocity function, we have 0 equals negative 32k plus v. This can be rewritten as 32k equals v. We can plug in 32k equals v into our position function. If we do that, we get 600 equals negative 16k squared plus 32kv. Now we can simplify this, or not kv, my bad. V is equal to 32k, so this will turn into 32k squared. That was my bad. Now we can simplify. We will get 600 equals 16k squared. Now if we divide both sides by 16 and square root both sides, we will get the square root of 600 over 16 equals k. Like I said before, we don't want to simplify this because we still want it to be accurate at the end of the answer, but now we have a value for k. And with this value for k, remember, v of 0 equals v, and we want to know the initial velocity. The initial velocity is just v, so if we could solve for v, then we'll have our answer. And we have an equation over here, 32k equals v, so if we just plug in this value for k for here, then we could get our answer for v. So, plug in root 600 over 16 into 32k equals v, we will get 32 times the square root of 600 over 16, and that's equal to v. And that's technically our answer. We do want to simplify because it looks like crap like that. But v is equal to 195.959. And remember, this was in feet, so it will be feet per second. And so that's a bit of a weird process, but that's how it goes when you're trying to solve for one of these points, one of the values in these points that were given, while you're also given some extra information. All right, we have three more problems I'm going to go over today, and this is the next one. So, an airplane starting from rest has a constant acceleration moving down the runway. This plane requires 4,000 feet of runway and a velocity of 240 feet per second in order to lift off. What is the plane's acceleration? So immediately we run into an issue. We're not given an acceleration. We're asking for what the plane's acceleration is because it's moving horizontally. It's not going to be gravity this time. And so remember last time how we said v of 0 equals v? We're going to do that same thing here, but instead we are going to be doing it with acceleration. So we are going to say that A of t is equal to A. And from this, we're going to check our other information and write it down right now. So it says that the plane starts from rest. If it's starting at rest, that means that v of 0 equals 0 and s of 0 equals 0. Because it's not moving, hasn't moved, and all that. And remember last time how we had like a v of k equals something and s of k equals something? This problem gives us that, and I'm going to write down that information now so we can use it later. So, it says the plane requires 4,000 feet of runway, and it requires a velocity of 240 feet per second. We don't know when it's going to hit those values, but we know it needs them. So this is going to be where for our points k. So v of k, it needs to be 240 feet per second to lift off, so v of k will equal 240. And it says it needs 4,000 feet to lift off. So s of k will equal 4,000. With that, we can proceed as normal, and we can use all our information to solve for acceleration. So, we're going to integrate a of t dt equals the integral of a dt. That will give us v of t equals at plus c. We can now use this first velocity value input. We will get 0 equals a times 0 plus c, and that will just tell us c equals 0. So, v of t equals at. Now integrating both sides of this equation, you'll get integral of v of t equals the integral of at dt. That will give us s of t equals at squared over 2 plus c1. Plugging in this information for c1, we will get 0 equals a times 0 squared over 2 plus c1. All this stuff cancels because it's multiplied by 0, so 0 equals c1. And that will let us be left with s of t equals at squared over 2. Now that we have both our velocity and position functions, I'm going to clean this up so we have more room to work. Now remember, once we get to the point when we have both our functions and our velocity position function and we're kind of stuck, this is when we use our extra points. So first I'm just going to plug them into both basically. So for s of t, we're going to plug in s of k as 4,000. So 4,000 equals a over 2 times k squared. And plugging in v of k is 240, we get 240 equals ak. So I'm going to isolate k. So I'm going to divide both sides by k here. And we get 240 over k equals a. Plugging that into this equation over here, like this, we are going to get 4,000 equals 240 over 2k times k squared, because it is k squared still. One of these k's cancels, and so we will be left we'll be left with 4,000 equals 240 over 2. 240 over 2 is going to be the same as 120. Don't forget we still have this k. So let's divide both sides by 120, and we will be left with, let me check my notes. Yeah, this is going to be give us that k is equal to 100 over 3. So now that we have a k value, we can plug this back in to our equation that was, where is it? Oh, so yeah, this one up here. Plug it into 240 equals ak. Plug this in to this equation. We will get 240 equals a times 100 divided by 3. And now using this to solve for a and simplifying, this will give us that a is equal to 7.2. And don't forget, we're going to need units. This was all in feet, and so it's going to be feet per second or feet per second squared because it's acceleration. And that is that one. All right, these last two are not that nice of problems, but they were given to us on a worksheet, so they could technically be similar on the test, so I'm going to go over them for you. First one says, a child drops a rock from the top of a 576-foot tall building. 2 seconds later, her brother throws a second rock towards the ground. With what initial velocity must a second rock be thrown in order to reach the ground at the exact same time as the first dropped rock? And now for this one, it's not going to be that nice, but what we're going to have to do is we're going to have to create an equation like the a of t, v of t, s of t. We're going to have to do that for both the kids, the first kid and the brother. So let's start getting to work with finding our information now. Now it says it's a 576 foot tall building. So both of the accelerations are going to be the same because it's just gravity, and because it's feet, it's going to be a of t equals negative 32. Because we're going to have different functions for the different kids, I'm going to write this twice. A of t equals negative 32. But to denote which kid I'm talking about, I'm going to put a small subscript right here. So a1 of t and a2 of t. Now we're going to find v1 and s1 and v2 and s2. These are just going to be our points that we use like we normally do to just solve for the particular solution. So it says that both the kids are dropping it off a 576 foot tall building. So that means for both of them, s of 0 will equal 576. Now the velocity is where they're going to differ. The first kid drops it off the building. And as I explained before, if you drop something, that means that at that point, its velocity is going to equal 0. But for the second kid, when he drops it, it says that he doesn't actually drop it. It says he throws the rock down. And so we don't know what velocity that's going to be, so we're going to have to write v2 of 0 equals v, as we did before. And I know other problems we have had, like the extra s of k and v of k to work with. We don't have that here, but we do have two different kids' equations, so we're going to be using that later. So what we're going to do is we're just going to start going through both of these as we normally do. So for both of them, we're going to integrate a of t, so it'll be integral of a1 of t dt, and that will equal the integral of negative 32 dt. Same for the kid over here. Integral of a2 of t dt equals the integral of negative 32 t, or negative 32 dt, I should say. So that gives us v1 of t equals negative 32 t, and v2 of t as well equals negative 32 t. Don't forget there's going to be a plus c on both of these, and because there's two c's already, we're going to have to start using the subscript. So I'll call this one c, and this one c1. Plugging in our information, for the first kid, we will have 0 equals negative 32 times 0 plus c. The second kid, we have 0, or not 0, we'll have v equals negative 32 times 0 plus c1. For this kid, we'll have c1 equals v. Over here, we will have 0 equals c. So getting our actual velocity equations, we'll have v1 of t is equal to negative 32 t. Over here, v2 of t is equal to negative 32 t plus v. Now we're going to have to actually integrate both of these and stuff, just like normal. It's a lot of stuff to just write. Integrating both of these, we will get s1 of t equals negative 16 t squared plus c2. Over here, integrating this, we will get s of 2t, or s2 of t, I should say, my bad, will equal negative 16 t squared plus vt. Don't forget integrating v, because v is a constant. We're just going to get vt, and then plus a c3 in this case. Now we are going to plug in these information stuff. Over here, we'll get 576 equals negative 16 times 0 squared plus c2. And let's just do this right now. 576 equals c2. And that means s1 of t will equal negative 16t squared plus 576. Moving on to this kid, we would plug in s of 0 equals 5, s2 of 0 equals 576. So it's going to be basically the same thing as the first kid. So negative 16 times 0 squared plus v times 0 plus c3. These things with the zeros cancel. 576 equals c3. So that means s2 of t equals negative 16t squared plus vt plus 576. Now that we have all four of our equations, I guess this time, I am going to clean up the board again and get back to you. Okay, now we have these four functions, but we don't have like an s of k or a v of k value to plug stuff into and figure out what we want to solve for. But we can use more information that we're technically provided to solve for this. So remember, we want to find the initial velocity such that the second kid who threw his rock 2 seconds later than the first kid such that both the rocks hit the ground at the same time. So what we should probably do first is find what time the first kid's rock hit the ground, and then we can use that to hopefully solve for other stuff in the problem. So to find when the first kid's rock hit the ground, that would mean if it hits the ground, the rock's position is 0, and that means basically setting S1 of t equal to 0. So if we set S1 of t equal to 0 and solve for t, we are going to get t is equal to 6. So it would be really, really nice if we could plug in this t equals 6 into one of these equations, and that would help us solve for v. The reason we can't do that is because these kids did not throw the rocks at the same time. So even though it's t equals 6 for the first kid, because the kid threw the rock, it took 6 seconds to hit the ground, the second kid, he threw his rock 2 seconds after the first kid. And we set our v of 0 at that 2 seconds after the first kid. So even though this is t of 6, because this kid threw his rock 2 seconds later, we're going to have to subtract 2 from this to get what the time is actually equal to relative to the second kid. So 6 minus 2 is going to equal 4. And so now we have t equals 4. This is correct relative to the second kid. So we can plug in t equals 4 into one of these equations. And we are going to want to plug it into the position function, S2 of t. And here's why. We know that at time t equals 4, that position is 0, because this is when the rock hits the ground. So because we know that, that will let us plug in a value for S2 of t, or S2 of 4, I should say, because that's going to be 0. And that will also let us plug in values for all the t's, because it's going to be 4. So if we do that, that's going to give us 0 equals negative 16 times 4 squared, plus v times 4, plus 576. If you notice this equation now, it's all a bunch of numbers, and the only unknown is v. And v is what we've been trying to solve for this whole time. So if we can just do algebra, plug it in a calculator, whatever we want to do, and solve for v, we will be done. And if we actually do that, we will get that v is equal to negative 80. And this is in feet, so it will be feet per second. I really did not like this problem. It was kind of ugly, and you really have to think outside the box for it. So I hope I explained it well enough for you, and you understand the process at least somewhat, in case we see this one on the test. But we have one more. So one more, and then we'll be done. All right, last problem of the day. It is 2 parts, but it's not bad that it's 2 parts. It's just the process that's the issue, but we'll get to that. This last question says, a model rocket is fired vertically upward from the ground. It accelerates for exactly 3 seconds with a of t equals 48t, measured in feet per second squared, at which time the fuel runs out. The rocket, of course, climbs for a few more seconds. So part A wants to know the maximum height of the rocket, and part B wants to know the total time the rocket's in the air. We'll get to those later. What we want to do now is actually figure out all the acceleration, velocity, and position stuff. And here, just like with the last one, we are also going to have to create 2 different equations. Here's why. So the first one tells us that a of t equals 48t, because it's accelerating vertically. But after those 3 seconds that it accelerates vertically, it's going to switch back to where it's gravity. So it's going to be a of t equals negative. This one is in feet per second, so it'll be negative 32. Now let's start looking for our velocity and position values. So it says that it's fired vertically upward from the ground. So if it's on the ground, that means that v of 0 is going to be 0. S of 0 is also going to be 0. And so with that, we can basically just start solving, because I'll tell you right now, these v and s values we are going to get from this equation right here. So let's just start going with this one. Integrate a of t dt is equal to the integral of 48t dt. This will give us that v of t is equal to, 24t squared, and then plus c. And then if we actually plug in this value right here, we get 0 equals 24 times 0 squared plus c, or c equals 0. Continuing, we have v of t equals 24t squared. Integrating both of these, we will get that s of t is equal to 8t cubed, I believe. And is that correct? Yes. Equals 8t cubed plus c1. Then we just plug in this information, but we get kind of the same thing. 0 equals 8 times 0 cubed plus c1. c1 is equal to 0, and we get that s of t is equal to 8t cubed. What we want to do here is remember, they say that this acceleration from the rocket going upwards, that lasts for 3 seconds. So if we plug in 3 to our position and our velocity, we know what the position and velocity are at 3 seconds. And those values are going to be our v of 0 and our s of 0 for this equation up here. So let's do that now. We're going to do v of 0, or not v of 0, we're going to do v of 3 and s of 3. And this is basically just calculator work pretty much, but actually both of these are going to come out to be 216, both of them. So v of 0 for our second equation will be 216, and s of 0 for our second equation will also be 216. And I didn't do it earlier, or throughout this equation, even though I did the last one, so I'm just going to write our subscript here now. v2 of 0 is 216, s2 of 0 is 216, a2 of t is negative 32. And so with that, I'm going to erase this, and well, I'll just do it right now. We don't even need a jump cut. We're going to erase this. We're going to proceed through the same thing with this one up here. So integral of a of t, or a2 of t I should say, dt, will equal integral of negative 32t. Or not negative 32t, just negative 32, I'm back. This will give us v2 of t is equal to negative 32t plus c. We used c and c1 before, so this is a c2. And so if we plug in this point right here to get c2, we'll get 216 equals negative 32 times 0 plus c2. In other words, this will be 216 equals c2, or v2 of t equals negative 32t plus 216. Continuing from here, we got to integrate both sides again, and that will give us s2 of t dt, or no dt, s2 of t equals negative 16t squared plus 216t plus 216. We can plug in this point right here, so we'll get, actually I went ahead of myself. This is not 216, this is plus c3. The reason I said plus 216 is because we're going to plug in this point up here. 216 equals negative 16 times 0 squared plus 216 times 0 plus 3. Those cancel. We get c equals 216, so I was just getting ahead of myself. So our s2 of t is just going to equal negative 16t squared plus 216t plus 216. So now we have velocity and position functions for the second one. We can actually start answering our questions. They want to know, what is the maximum height of the rocket? So the max height of the rocket is going to be when the rocket, its velocity is 0. Remember, maximum height means that velocity is 0. So if we find when velocity is 0, find that time, and then plug it into s of t, then we'll be set. So I'm going to erase the board and then get ready for that. Okay, clear the board. So remember, we said we wanted to set v2 of t equal to 0, because when velocity is 0, it's going to be its max point. We're going to solve for t. So if we do that, we are going to get that t is equal to 6.75. T is equal to 6.75. And then now we can plug that t value into our position function. So plug in 6.75 into s2 of t, because we're looking for the position at that time where it's the max height. And then that's going to be our answer. That is going to give us 945. This is in feet, so 945 feet is going to be our answer for part A. Now part B. Part B asks us, where was it? It asks us, what's the total time the rocket's in the air? And so, what we're going to have to do is we're going to have to find the total time it's in the air here, total time it's in the air here. The first that first function, that's really easy. It told us that it was in doing that going upwards acceleration for 3 seconds. So for this function, it was in the air for 3 seconds. Now if we find the time it's in the air for this function, add these two together, we'll be fine. So if we want to know the full time it's in the air, we're just going to have to basically find when it hits the ground and then that find the time it hits the ground basically, and then that's going to be our time, whatever. So if we set S2 of t equal to 0, because that's when it hits the ground, that's going to give us a time, and that was the whole time that it's falling. Because remember, it started in the air. So when it equals 0, it's going to have gone up a little bit more, falling all the way to the ground. That's the whole time it's in the air. So if we set S2 of t equal to 0, it's going to be 0 equals this mess. That's not nice. That's the thing you plug into your calculator, and you will get that t equals 14.435. So if we add 14.435 to 3, we will get our answer for part B, which is t equals 17.435. And that is our answer for that one. So working with all these word problems, the process is very similar for a lot of them. We're just going through, finding our points, integrating a lot of stuff. So in that sense, it's not that bad. The main issue is finding all of our information and figuring out how to work it all together. So I hope I did a good job explaining all that to you, and good luck with all these problems.